My name is Matthew, and I'm excited today to be here. So we're going to start the conference off with a bang. Our first speaker, Travis Oliphant, needs no introduction, and he'll be talking about Conda, a build and dependency management system that has saved my life several times. And if you don't know about it, you should be excited. So Travis, come on up.
Thank you, Matt. Wow, music. My goodness, I feel like a rock star. It's great to be here. Thanks for coming to visit this talk. I know there's a lot of exciting talks, and it's tough to decide which. I hope that you won't be disappointed. I'm really excited, and I talked quite a bit about Conda. There's some jokes, actually. Last time at the last PyData New York, we were running a session, and every question I kind of responded to, yeah, Conda does that, yeah, Conda does that, yeah, Conda does that. I mean, of course, there's a lot of details and a lot of things you may have to configure to make sure it works. But I'm really excited about Conda because, frankly, it solves a lot of problems that have plagued the scientific Python ecosystem for decades. And they've been at the heart of a lot of problems that I've personally known about and personally been involved with. So I'm really excited about it because I feel like we finally have a solution that really takes a lot of pain away from a lot of other people as well. And we're still trying to get the word out. We're still promoting it more and getting more documentation together. It has a lot of functionality that a lot of people still aren't necessarily aware of because it does not necessarily broadcast as far and as wide as it could be. Now, if you're an Anaconda user, you already have Conda, although you may not know of all the features that Conda can provide for you, because that's how you get the distribution. It's Conda's underlying package manager for the distribution, as we'll talk about. But I want to motivate the discussion a little bit by talking about the big problem, which everybody's facing. We just saw a great talk from this data scientist, Uber geeks, data geeks at Facebook, showing how many open source tools they use, then they also contribute back. And that phenomenon actually exists on every company, almost every company out there. They're using data science tools, they're using open source tools, and also contributing back. And what that's doing is exploding the number of available tools. It's just growing. And so how do you actually use these tools? People want to use these tools. They say, hey, other people are doing the work that I otherwise I'm going to have to spend money doing. I ought to figure out how to deal with it. But it's not about just using it once. It's not about, okay, I grabbed it, I got this version of NumPy from 2007, I'm done. No, because it's going to change 6 months, 1 year, year and a half. It's going to change how you're going to manage that change process. The big challenge is that a fundamental principle of software engineering is that separation of concerns, which you want to separate components in different pieces, but you have to bring it back together. And then sometimes that creates these deep dependency hierarchies. And so you end up with a dependency graph that might look like this, where you've got just thousands, potentially deep, of dependencies in a very large complex system. How do I deal with that in a real way? So I call entry points kind of that end user application or that end user script. There's a final point at which you use, this is what I want to accomplish for my application or my process. But I have a lot of dependencies that it might have, and those packages themselves might have dependencies. So you end up having different, they need different versions. The other problem is one person on a system, in a single machine may want one version of a package. Their particular dependency tree requires one version of a package. Another person on the same system requires a different dependency tree, different version of another package. This problem is actually not specific to Python. A lot of times we complain about the Python packaging problem, but it really is because Python has been at the leading edge of integrating lots of different things together. You look at the SciPy stack, for example. We're calling out to Fortran code. We're calling out to C code. We're calling out to native code from every stripe. And so we've kind of been at the forefront of this fundamental general problem that every language deals with, including R, Ruby, Node.js, all of them do. They all sort of half solve it to one degree or another. The fundamental tension is that production deployment needs usability, stability, needs testability, needs reproducibility. IT managers want easy deployment, want to be able to test it, understand how to back up to what they had before. On the other hand, developers want agility and easy development. They want to be able to use the latest package from the latest, greatest open source piece that's come out. And they want to do that quickly. And so how do you kind of resolve this challenge? And I think that's the fundamental challenge in the face of anybody trying to take advantage of open source. And I don't think you can take advantage of open source fully unless you address this. So kind of the fundamental principles, complex things built out of simple things, we've addressed all of this. To deploy the systems, you want to separate everything out for development ease, for maintenance ease. But when you actually come to create an application that's something that does something useful in the world, you have to bring it all back together again. And how do you do that? You need a good package system. And that means you need good binary artifacts. a place to store them, a place to hold them, a place to connect them, a place to deal with them. Andrew needs something, this notion of multiple environments that virtualenv has popularized in the Python ecosystem, but it's kind of a fundamental principle that even operating systems should really get behind and are starting to get behind. You see from Red Hat the idea of software collections emerging. You see other kind of packaging systems promoting this idea of multiple environments. It's no longer I have a system and I have one version of Python installed, or I have one version of NumPy installed. It's, okay, for this particular application stack, it needs these dependencies, and maybe there's a handful of applications that use all those dependencies. All right, so I want to talk about how Conda actually is a really helpful solution to a lot of these problems, and that with Conda as a base, you can do build a lot of great systems. And so all of this is free. This is all free stuff from Continuum. We like to give away free stuff. We do have to stay in business, but I'm not going to talk about how we do that here. I'm going to talk about the free stuff we give away. Conda is an open source BSD licensed package manager. It's free. You can contribute, join the community, help us make it better. It's on GitHub. It is a basically cross-platform package manager like Yum or apt-get. It uses dependency management. It creates a system-level environment notion, which is an amplification of Python's virtualenv to actually system level. So it doesn't just mess with Python path in order to set up your, where it's going to load modules from. It actually fundamentally deals on a system level. We have Anaconda, which is the full distribution. A lot of people just download Anaconda for a single-click install of a bunch of packages. But it's really a combination of what we call mini Conda, which is Python plus Conda. So Python plus the package manager. And then from there, you can do anything you want. You can build whatever dependency tree you'd like, including the Anaconda distribution. And then another one that's actually not as well known because it's still in beta, and we haven't popularized it very much, is something called binstar.org. Binstar.org, its purpose is to be a package repository for everybody. And if you're willing to give your packages away, if you're willing to let people use them and download them for free, it's completely free. And it will always be completely free if you're willing to give your packages away. So binstar.org, it integrates tightly with Conda, so you can easily release your binary packages and make other people be able to get your particular dependency set. All right, we do have some premium offerings here. They're in the slide deck, but I'm not going to go over them. I guess just maybe to help people understand that we do give things away for free, and those are going to stay giving away for free. And there's no kind of bait and switch thing going on here. This is what we're selling. If you want those things, great, but this stuff that's free is going to stay free. So Conda is one of those things. It's cross-platform, and essentially what it does for a cross-platform system. If you're just using Linux and your whole environment is Linux, then Yum, apt-get are pretty good. They lack the environment notion, actually, that Conda has. But for a lot of people, when I was a developer of NumPy and SciPy, it was interesting to watch kind of the different platforms and kind of the pressures that were there. And I never had complaints from Linux users once apt-get showed up. And all of a sudden, it was like, oh, sure, you can release a new version of NumPy. I just use apt-get and get everything I need. But the Windows side, it was always a struggle because people would spend hours and days building up their ecosystem. They went, oh, man, a new release. I don't want a new release. It was a big problem. So Conda really solves that because it provides the same functionality as an apt-get or a Yum with the addition of environments across platforms. Now, there are a few of these package managers on Windows. They're not as well known. Things like Chocolatey, NPACD, and a few others exist. So what does Conda provide you? It has excellent support for system-level environments. In a lot of ways, these are like mini VMs. You see a lot of the energy around Docker I/O. People are going, oh, it's exciting. I can just virtualize a box. Now, if that box, if all you're doing is creating a collection of files together that work together, Conda environments just do that just fine, and it's much faster and it's much lighter weight. So they're really they can replace your usage of Docker in many cases. There's just an overlap of functionality there. It minimizes code copies. I mean, one approach to that would be just to copy whole trees over, right? And we do that if we need to, but where possible, it uses link farms, so hard links and soft links, depending on exactly which is possible. It uses a dependency solver. One big difference, one big thing that's missing from the Python, from PyPI, for example, is a metadata server. Right? There's information about dependencies. You can't actually know that on PyPI unless you traverse and download all the packages. So that metadata server that tells you the dependency graph is already available in Conda and part of every Conda repository. And we use a dependency solver in order to provide satisfiability. The format of a Conda package is dirt simple. It's very simple, so anybody can build one. We have some tools to build Conda packages, but you can build your own as well. There's nothing stopping you from just creating your own. It's just a tarball of the binary that you're going to install. And then there's metadata that's easy to allow static analysis. It's easy to create these idea of multiple channels, so you can actually have things coming from multiple things. One big reason people like Anaconda is it's user installable. Conda allows you to install in your own directories, your own private installation of any environment. You don't have to get permission from anybody to start. And then the other piece is you can use pip with Conda as well. We're not taking anything away. You can still use pip to install things that if you don't have a Conda package for it, go to your environment, just do pip install if you want to basically source build or else build from a package that's available on PyPI. And that works just fine. So here's a simple example. Let's say I want to set up a test environment. Conda update Conda will just make sure you have the latest version of Conda. You don't have to write that, though. Conda create, -n. Conda create is the fundamental way to create an environment. -n tells you to create a named environment. Named environments are stored in a particular directory. An environment is just a directory on your path. It's just a place that's basically like /. It's like the prefix, the main prefix for a change root jail or something. That creates a directory called test somewhere, but an environment called test. And then I'm saying install Python and pip into that directory. So Conda is actually general. It's not Python specific. So when you create an environment, you have to tell it what you want to install. You could put R, you could put Node, you could put anything that a Conda package is available for. So Python, pip, make sure those are there. And then I want to, how do I use that directory? Well, how do I use the Python stored in that environment? Well, I could call it fully by expressing the entire path, but a common approach, especially on the command line, is to use this source activate notion which really changes your path. Just change your path to make sure that bin directory is first on your path. On Windows, the script's a little bit different. Now, once I'm in that directory, you can see it's a little bit different because of the test that's before my little prefix. Now I want to install a package that might be difficult to install from source, like scikit-learn, because I'd have to download NumPy and SciPy and I'd have to build, and I don't have a build, and if I don't have a build system on my computer, it's going to be a pain. And that's basically the fundamental complaint most people have, besides maybe the time it takes to do the build. But Conda install scikit-learn goes out and grabs the binary package for your platform, installs it quickly, easily, and you've got a working scikit-learn. This is true for IPython Notebook. This is true for for pandas, any of the things that people use. Now, maybe I want to create a different environment, right? You can create as many environments as you like. We have this notion of environments are throwaway. They're free. You can just have as many of them you want. Here's an example where I'm actually creating a Python 3 environment. So Conda, it can be a little confusing because Conda is based on Python, but I'm creating a Python 3 environment. So the way to think about this is you're building, like a new language. You're building a new bin directory and put anything you want in there. And I'm going to put Python 3 in there. So I put Python 3 in that new directory, activate it, and then I can actually install IPython Notebook into that Python 3, and I can have an environment where I'm testing out Python 3. That's as simple to switch between as every other environment I have. So it's really easy to use Conda to kind of go back and forth between Python 3 and Python 2. It can really help you kind of identify and understand the differences. Or you can do this all together and you can have a command line that's very, very long that puts all the packages you want to install. Now, you don't have to put every package that will be installed because the dependency analysis will grab all the dependencies. So you typically just put I want Python, I want IPython Notebook, and then whatever it needs to install those. And those will all be installed. So an Anaconda installation is really simple. You have a root installation, and it has basically a package cache /pkgs. I'm not going to go over this slide in too much detail. Basically, at the bottom, you see it has a bin directory, has a lib directory, include all kind of the basic user directories you might have. On Windows, the path locations are a little different. You have a scripts directory. You still have a package cache directory. The package cache is where all the tarball is downloaded and then unzipped, basically, untarred. And that's the package cache. And then you have environments just linked to it. And so it's a very straightforward approach to building large-scale environments. Now, if we look at an actual Conda package, we see that it's just a bzip compressed tar file. That's the extension at the end. The package name is everything. You have this package name which can have anything in it. And then you have this version number, and then a build string, which is not really used by Conda, other than perhaps the last integer, which is a build number. The version and the package name are what is used by Conda to resolve dependencies. Now, if you look at a Conda package, it's just it's just a packed tar file of everything. If you were to take your software and install it into a system, and then did a diff between the disk that you installed when it started and then when you installed it, did a diff and looked at that, that would be the Conda package. You'd have the full path to everything up to basically the prefix where you installed it. So it's a lot like basically everything in your system that has different because I installed this software. And that's all zipped up together or tarred together into a single package, tar file, and then b-zipped up. And that's a Conda package. So an environment is exactly a union of all those environments. In fact, if union file systems were more popular and more common, you would just implement this as by unioning all these little packages together. And that would be an environment. Environment is just a simple union file system of these individual Conda package file systems. Now there's one more thing a Conda package has, which is this info directory. It's the metadata. And there's only 2 necessary pieces of metadata. There's others that can be there. There's only 2 that are really necessary. One is the files list, just basically a manifest of all the files that are installed. And then the other is an index.json, which has dependency information. It's pretty lightweight, only has a little bit of dependency information. So that's it. Everything else in the Conda package is just whatever happened to need to be installed. Maybe stuff in man, maybe stuff in bin, include, lib, share, whatever. Now, a big thing I really love about Conda, and I really promote because I think it's an incredibly important idea, is environments. And I relate it to the incredibly important idea of namespaces that Tim Peters put in the Zen of Python. Type import this, you see namespaces are one honking great idea, let's do more of those. Environments have a similar feel. They're one honking great idea. I should isolate my programming to a namespace, to an environment where I can be isolated from everything else. Because that tends to be a challenge you face when you're trying to deconvolve the workflows. There's a lot of uses. This is just a few. Reproducible science was the main motivating use case that we had when we created Conda, these environments. I want to be able to take something somebody's done. Maybe they have an IPython notebook. I want to know all the packages they need. I want to be able to reproduce that on somebody else's system and have all the specification needed so they can do that very easily. And with Conda, that's possible, and it's how we do it. Testing is another big use case. So a lot of times when you're using Conda, you have to kind of remember kind of where things are. Conda info is sort of your basic workhorse, or giving you information about, okay, where are my environment directories? Where are my packages stored? How many do I have? You can get the named environments you have with Conda info-e. And sometimes if you're debugging particularly, we love it if you send us a message that includes Conda info-all, so we can kind of see your setup and your configuration. To install a package, we've seen this. It's very, very simple. Conda install. If you don't give it a named environment, a lot of times you'll see just Conda install something, then it goes to the root environment. And a lot of people, that's what they do. They install everything into the root environment. That works great. It's good to know that there's environments exist so you can go beyond just everything in one big environment. So that's the -n. And currently, so in Conda, there's package repositories you point to. Now we'll show later how you can modify which repositories it points to. You can create your own repositories. By default, Conda will point to the repositories that we make freely available at repo.continuum.io. Now how it works is these repositories, we call them channels. So channels are basically a big directory of Conda packages with a little bit of metadata. This metadata information about dependencies of all those packages. So you can kind of just read the metadata to infer what you have to download. And those channels, when you do a Conda command, the first thing it does is merge the metadata from all your channels into one big metadata. So it knows, oh, okay, these are all the packages available to me. I can see where to get it. And then it uses that to go grab the particular downloads if it needs to. Perhaps you've already downloaded it, doesn't need to download it again. So if you want to create your own channel, which is a very popular use case, because maybe you have your own software you want to release, and you want to kind of use this same system. There's 2 options, roughly, that we've supported. Of course, you can do a lot of things yourself as well. But it's very easy for option 1 just to create a directory of Conda packages that live somewhere. Big directory of tar.bz files. And then run Conda index. The Conda index command on that directory will build that metadata. And it'll build just a metadata file that sits in that directory. And then you can either use, if it's on a system that's on your disk, you can just use a file URL in the Conda, when you're specifying a channel to Conda. Use file in your Conda RC file, as we'll see later. Or just use a simple web server, like simple HTTP server on that directory. And then you have a Conda channel that you can point people to. It's very, very simple to build up a repository channel in Conda. Option 2, if you don't want to set that up, is use binstar.org. It's very easy to do binstar upload of your package, and now it goes to a channel that you've constructed. And there's an on-premise solution of that as well with Anaconda Server. So those are 2 options to make channels. So binstar.org is still in beta. It should be out of beta likely within a month. It's coming really close. We're just trying to make sure that it's a couple of the idea of a frozen channel is finalized, basically. Once you have a bin-star channel, it's very easy to get one. Just request an invite. Wait anywhere from 30 minutes to 8 hours, depending on who gets to it, and we'll pretty much approve those invites. Conda install-C will allow you to tell it a channel name, and it'll automatically put the bin-star HTTP in front. If you would like to fully specify your channel name, because maybe you have it running on some other web server you constructed with Conda index, you can do that too, and Conda will take that channel as a place to look for Conda packages. But it's very easy to integrate with bin-star. Conda install-C, channel name, package name, and then it will install from your package. So this is a very, very easy way for you to make software, point people to it, and have them have a successful instant download. Right? It's really, really straightforward. I'm really happy about that because I feel like we've solved the problem. I feel like we've solved the problem that's plagued me, that's plagued the entire SciPy community for a long time. Now there's a lot of flexibility around that, and I'm looking forward to the kind of solutions that will emerge that can use these technologies. Now, a lot of times when you're using your Conda environment, you want to kind of see what's installed. See, there's a Conda list command. Now this command will also look at your packages that weren't installed with Conda. Maybe they were used, maybe it was Python setup.py, maybe it was pip. So it'll actually list those packages as well with Conda list. And you'll see the pip instead of a build number. Now, quite often you want to update. You want to figure out where you're going next. It's very easy to say Conda update pandas, for example. Conda update scikit-learn. It'll go download the latest version and install it into your environment. Simple as that. Now, there is a caveat. Sometimes people will go, okay, I'm going to Conda update Anaconda. That's not the right way to update Anaconda. So Anaconda is a collection of packages that are all tested to work together. It's what we call a meta package. It's a known stable release of all the versions. And so when you say Conda update Anaconda, it will go to the latest Anaconda meta package, right, which is a collection of specific versions of your other packages. So if you've gone into your environment, updated pandas, updated scikit-learn from a base Anaconda, and go back and say Conda update Anaconda, currently it'll revert back to your Anaconda release. So it's not often what you want. There is a command called Conda update --all, and that will actually go out and look for the latest releases of everything in your environment and try to download those. So there's a little bit of miscommunication sometimes. People kind of expect a different use case, and we'll keep working on the usability there. It might be that we sort of raise an error or something if you have different things in your environment. So you can search for a package if you're just looking for kind of a regex that you have. I want to see, is there a package that's something like num? What are the num packages, or what are the typo packages? Conda search typo. You can actually add an outdated if you want to look for only packages that are installed but outdated currently, kind of that have new releases available but you don't have them. You can also do that with the searching. You can remove files. So you can now removing is a little bit different than you might think, because removing unlinks from your environment. But there may be other environments on the system that are using that package. So it doesn't delete the files. It doesn't delete the files from your file system. It's just your environment no longer sees them. That's what remove does. And you can give it a -n for the environment name as well as the packages that you want to remove. If you actually do want to remove unused packages, then there's a Conda clean -t and a Conda clean -p that will remove the tarballs, the cached tarballs, and then P will remove all the directories as well. So it'll just eliminate from your system, from your machine, all of the packages. And then you can remove an entire environment, Conda remove -n -all. You can just delete all the directories. You can just look at a directory structure and delete the whole thing. The remove command will actually run potentially pre-uninstall scripts that a package has. Because it might be that a package that's installed might need to do some other cleanup that they've defined. And so the -remove will make sure that gets run too. Rather than just deleting the file, maybe you leave some state in some database somewhere, some registry somewhere the package had to construct. It's very flexible what a Conda package can do. Now, another little use case for Conda that's pretty clever, I think, and actually fairly useful, is this idea of I can go make an environment and then kind of do whatever I want. I can Python setup.py install, I can pip install, I can kind of do what I want to build that environment, what exactly I desire, and then it'll have a collection of untracked packages. Conda package -u will show me this list of all the packages that Conda doesn't know about, that are kind of apparently you installed them without kind of tracking them. Now, if you use the Conda package name and actually say, give it a package name, give it a package version, it'll take all those untracked packages and build you a Conda package that contains all that information and allow you to then ship that to somebody. So it's a very easy way to sort of do whatever you want in your environment and then reproduce that by constructing a Conda package and ship it off. Now, I kind of talk about it as pickle for code. In much the same way, pickle is a nice way to serialize data that you're going to kind of throw away and not really persist forever. Pickle is not a good way to persist to large data structures. In the same way, this approach to Conda packaging is also, it's a very nice way to kind of send a reproducible environment around for temporary uses. But a lot of time, but it's not the best way to sort of package a Conda package that you want to redistribute for a long time. Because unless you're careful. Like you have to be careful to make sure that only the package you're trying to package is in there. A lot of times, for example, if I did pip install of a scikit-learn inside of a basic Conda environment, then it would go and it would download scikit-learn, it would download scipy, it would download numpy, try to build all those things, and it would give me a large collection of files. Then if I just said Conda package, I would create a single package with all that stuff. It would not be separated into the individual granular components that it really should be. So that's the kind of thing you want to make sure you're understanding the difference. Now this Conda RC file we talked about briefly in the past, this is how you configure where Conda looks for channels. This is how you configure what proxy servers, if you need a proxy server to go out to the internet in your location. This is where you configure where are the environment directories. So these named environments, where's it going to look for those? You can configure where those are. You can configure where your package cache is. When I download packages, where will it actually go and untar the directories? And there's various other things you can set. There's also a scripting interface to this. You can edit the binary, you can edit the text file if you like, or you can use the Conda config command to add keys to that file if you sort of want to script this or create an interface. Now, like I said, Conda packages are a great way to install your software, and it's really nice to kind of have a community of people using a similar way to install complex software. But to do that, we need people to build packages. So there's some neat facilities, some fairly useful facilities to build new packages. I mentioned the format of a tar.bz file is very simple. And as long as you construct a directory, tar it up, and bz2 compress it with an info directory for metadata, you have a Conda package. And you can do that however you want. Feel free to make whatever tool you want that does that and builds it. And Conda will use it just fine. It doesn't need to be built by Conda build or Conda pip build. But these are tools we've created to make it easy. So that you can, for example, if you know, oh, there's this package on PyPI. Like yesterday, I saw the planout talk, for example. And planout was a great new tool. It's on PyPI. I said, well, I wonder how hard it would be. And basically within a minute, I had Conda packages for planout. And they're currently on my channel. And as I'll show you later, actually, there's a convert utility because it has only Python code. I can actually make a Conda package for every platform very easily. And they're all on my channel now. And it took about 2 minutes to do the rest of that. So it's very easy. If anything's available on PyPI, Conda skeleton PyPI, you give it the name of the PyPI package, and it will construct a recipe directory for you. Now you can go in and modify that recipe. Recipe is just a directory with some scripts. But usually it's enough just to take that default recipe and Conda build the recipe directory, and you get a Conda package. But one that's also modifiable. You can go and check, make sure the dependencies are right, make sure that it's guess about what the dependencies were. Conda skeleton tries to use the information that it can from PyPI. It's a little bit hard, actually, but to go and figure out what the dependencies are, make sure you have those. Conda build will actually create a separate environment and build everything in that separate environment. And then it will create another environment to test everything, right? To verify that what you're building is relocatable. It's not tied to any specific place where you've installed it. That's one of the things we really try to promote with Conda. While you can have a Conda package that is not relocatable, you just are going to be forced to install it into an environment that has a particular path. Like that would be the case if you did not have a Conda relocatable. We really try to promote relocatable packages because that's the only way to take full advantage of the environment notion. That I can just move these around anywhere in my system. Now option 2 is a recent addition. There's a Conda pip build. So basically if pip can install it, the Conda pip build can pretty much usually build a Conda package for it. And all this does is it creates a separate environment, installs Python, installs pip, and then pip install your package, and then takes essentially that package that untracked packages in your environment and bundles all that together into a single download. It's actually a little more clever than that because it tracks dependencies, and if pip tries to grab a dependency, it'll actually go out and separately build that as a Conda package on its own. So it's a little more intelligent than just what I described, but basically it does something like that. So recipes are the key to building Conda packages. A recipe is just a directory. You have build.sh, Build.bat, there's 2 files there. And the reason is because the POSIX, like Unix and Linux and Mac, are so different typically than your Windows recipes. And so rather than have a big one file with a big if statement in it, we just have 2 files, bld.bat and build.sh. And then there's a YAML declarative file that describes the dependencies, describes the runtime dependencies, the build dependencies, the package name. And then optionally, you can have a runtest.py file. That will be executed during test phase, just a file that when you build the package, it'll execute that and make sure it passes. There can be patch files if you need to patch the source for any reason. And then any other resources needed can also be stored in that directory. Here's an example of recipe metadata. Now, there's other approaches to this too. We basically have an approach where a metadata file can be a template. And it can be stored along, just sort of right next to the setup file, and it can be called automatically. So you don't have to kind of duplicate information in both places if you have a Python file that you're making. But it's important to remember that Conda packages are bigger than Python. Python packages, you can package R, and we have nascent R packages for Linux 64, for example. So you can run R and install them in your environment just like you can with Python. So we have this general approach to building recipes, and it's a declarative approach. Now, quite often, there's a lot of packages out there that really just that are just Python files, or they're just text files. There aren't any really binaries in it. On the other hand, we've built Conda packages to be so simple that they can't be really cross-platform because it's just a tarball of what's installed in the file system. So, for example, in the Windows system, you have C:, you have this different path structure. You have scripts instead of bin. And so a Conda package, even though it consists of just text files, and the text files are the same on both platforms, you do have to have a Conda package for a different platform. Disk space is cheap, so we went that direction to make it simple to build these things and simple to install them. So on top of that, we created this utility called Conda Convert. Conda Convert will take a package that only has Python scripts in it, or it basically has no binary files inside of it. Or at least .sos and .pyds, .dlls. And it'll convert it from the package you are on to the package you want. This can run on any system. So my Mac system, I could build the plan-out packages for Windows 32, Windows 64, Linux 32, Linux 64. Because really all it was a metadata change and a file system rewriting. And then I can upload those to the directory. So this is a simple command, Conda Convert. You give it a directory, it'll store in there. You give it the top level directory, and it'll store Win32, Win64 subdirectories. And then once you have that Conda package, there's a simple bin star upload. In fact, the Conda build command by default will ask you if you want to upload a bin star. You can turn that off in the Conda RC file, say bin star upload is false, and so don't do that. But by default, it makes it very simple to build a package and make it available to everybody. And so if you look at my binstar.org/Travis, for example, you'll see several thousand packages. I've been playing with them. Not saying that all of them are fantastic. But I actually made another account called Auto, where I've been doing some auto conversion. I converted about 18,000 of the PyPI packages to Conda packages under that Auto account. Again, they're all beta. They're not necessarily well tested, but they're automatically built. Now, once you have this repository, then conda install-c Travis, you don't have to put the full path name. You just say -c, whatever the username is. So conda install-c Travis, package name, and now Conda will go to the binstar account of that user to get the packages, or add that essentially to the Conda RC file. Now, here's how you can use Conda config. Here's the particular keys you add if you want to add a particular channel to so that every time you run Conda, you go to a particular channel. Conda config --add channels. This is how you add Travis's directory. There's another person, Aaron Muir, who's built quite a lot of packages, especially for OS X. PyQt, for example, is up there. And then you can get packages from other people, other users. If you want to upload packages, you first register the package and then upload. You can actually just upload the package and it'll go to some defaults. It'll basically become a personal package that you're sharing. As we'll see, there's a couple of notions in Binstar. There's 3 different notions of visibility of packages on Binstar. There's this idea of a private package. And a private package, you're going to have to pay for if you want private packages after the beta period. Currently, you can get them for free. But that is what's going to not necessarily be free in the future. Personal packages, which are public, which anybody can see, totally free, just fine. That means this is your kind of private, this is my build. Then there's the idea of a published package. The idea of a published package is this is kind of the package author or the package maintainer or somebody who's committing to create the binary for that package should be publishing there so that people can add that public channel, and that will be a default sort of known quantity of where Binstar, of where good Conda packages can live on Binstar. So you can imagine personal kind of being a Wild West of people's individuals, or maybe it's somebody specific, a set of packages that work for a specific thing. And then publish is like PyPI with Conda packages. Useful aliases, not necessarily needed. Anaconda server is a product we do sell. But that's basically the talk. I'd like to thank the people involved. There have been Elon Schnell, principal Conda developer currently, Anaconda developer. If you're using Anaconda, he's been building Python packages for a long time, and he's quite expert at it, actually. It's a unique skill. If you're interested in building Python packages, come talk to me. We're always looking for people who are good at this, because it sort of takes a lot of nuances to figure out how to build on Windows and Mac OS X and all the rest. Brian Vandeven, who's currently author of Bokeh and principal contributor to Bokeh, started the Conda project, actually, and one of the original authors. Sean Rossross is the principal Binstar.org developer. And then Aaron Muir is a Conda and Binstar developer, currently at Continuum. Now, there are other contributors as well to the Conda resource. And I'd like that list to grow longer, so next time I give this talk, I can actually show a long list of Conda contributors. But these are the folks that have started it off. All right, I'll take any questions at this point. Yeah, let's start in the front. Do we have a microphone, maybe? Yeah.
The one place to go to get tutorials and documentation on all this.
Conda.pydata.org. Thank you. Conda.pydata.org. The tutorials are actually growing. There's an FAQ now. It's improving. But it could be better, but it is improving. And then also Conda-H. There is quite a bit of online help. A lot of what I've learned about Conda, actually, I've learned by just Conda-H and experimenting. So it is helpful. We have the back in the back.
A couple of questions. First, what's the interaction or the relationship between Conda environments and the virtual environments, Python virtual environments? And okay, I'll take the next question later.
Okay. Yeah, they're separate concepts. So Conda environment, so virtualenv is it's a nice project that allows you to kind of create Python virtual environments. Conda environments are system level. So you can have an environment that has R in it, and it has an R view in it, for example. Or you can have a Python environment that has Python 3.3. Right? virtualenv doesn't let you kind of make a Python 3.3 environment inside of it. It's sort of just Python specific. But kind of abstractly, they're similar conceptually. But implementation, they're quite different, the way they're done, and then Conda is more general.
Okay. The second one is there are now the Python wheels packages, which are binary packages, and then it looks like Conda packages are similar in concept, maybe. So can you talk a little bit about that?
Yes, there are some overlaps. So with the wheels, then finally pip is getting closer to be able to do the things that Conda can already do, I guess. So it's a good question. If people want to make wheels, that's fine. You can make Conda packages from wheels as well. They're different. Like, if you talk to our Conda developers, they'll say one thing. I think the Conda package format is simpler, easier to build them than it is to build wheels. But wheels, for example, there's a bdist wheel inside of a Python setup.py. There's a way to do that. So I think it's sort of generally good to have, I like the fact we have more binaries available. And I talk to Nick Coughlin all the time. We were at PyCon recently just talking about kind of what's the difference. And the way Nick describes it is he considers Conda to be an integrator's tool. Right? If you're using pip, including wheels, including the pip package, the source packages on PyPI, you are an integrator. Like, you are a self-integrator at that point. Conda is a solution to handle the integration for you. Right, so I would say without wheels, Conda is the only thing to solve that problem. With wheels kind of solve the problem a little bit, but they're missing the metadata still. The metadata 2.0 is what they're moving towards. And so that's my perspective on it. I think wheels are a little bit redundant at this point. I don't think they're necessary, but they have some momentum, and people there's ways to build them, and that's fine. So they'll exist, and we'll make Conda packages out of them, very simply, I guess. Yeah.
I recently ran into a problem trying to pip install a package that depended on OpenSSL, which was installed by Conda. Is that a limitation of Conda that you can if you have a Python package that depends on a C library installed by Conda, that can only be installed by Conda in order
No, I
for
don't
it
think.
to work?
Yeah, let me know. Let's file an issue about that. It's not. It shouldn't be a limitation, but there's always surprises that show up, right? That's not intentional. It shouldn't be that way.
Yeah, we've told Aaron about it.
Okay,
but
great.
it hasn't been resolved.
I'm not clear why that would be. It shouldn't be the case, right? Unless maybe there's something that Pip's looking for specifically that we're not aware of yet. Or
it ended up having to do with like relative paths in the C libraries that Conda had installed, and we had to set like a dynamic library path in order for the binaries to see those, and it just didn't seem like a very good solution.
it could be. So for example, it could be that there are some, for example, Python packages that pip uses, the setup.py, might be looking for certain C libraries in a very specific user directory. Like this notion of relocatable binaries is a powerful one, but not everybody sort of is cooperating there, right? So I've seen a lot of recipes, for example, that have very hard-coded, I'm going to look in user lib something if I'm on Linux for the OpenSSL library.
No, it definitely wasn't that.
Okay.
It was kind of a dynamic library lookup problem, and it appears to be definitely related to the way Conda had installed OpenSSL in this situation.
Okay. Conda doesn't actually, all it tries to do is make it relocatable. So it just actually, rather than using LD library path, it uses relative paths. So definitely we should look at it. But again, this notion of relocatable is kind of a new concept. I think it's a valuable concept, but it's not familiar to, and it's not common the way people typically build. And so, yeah, there's a lot of interactions like that could exist, but it should not be the case. Those should be all resolvable. So thank you for bringing to our attention when they come up.
So building on the concept of being more of an environment manager and not just a package manager,
Yeah.
what are the facilities or plans to allow, well, I don't just want to get, NumPy 1.8, I want to be able to do Conda install my package from my master branch on my GitHub repo.
Ah, right, yes. No, that's a good point. That's a good question. Essentially, you want to do the build. The challenge is you want to essentially create a package from the Git repo and then install that, kind of all in one fell swoop.
But I don't want to go do the manual package creation stuff.
So. Right. So basically a tool, like the Conda build command should be able to accept a URL. I mean, I would say that's a feature we can add to a Conda build. One thing we've done actually is to stabilize Conda itself is separate it out. So just like Git, when you say Git and then give it a subcommand, it'll actually look for a Git dash. So if you try Git log, for example, it'll look for Git dash log as a binary. We do that with Conda as well. So Conda build actually runs Conda dash build. And that's a separate package now. So Conda dash build is its own package you can install separately. So things like this, I would love to see better tools for Git integration. Right now we have internal developers. We use Conda internally for everything. And so we use it for deployment, for releasing. We've cut ourselves on a lot of the corner cases. And I'm sure not all, but we've been trying to kind of make it more and more robust. And that use case has come up, and we're working around it currently with sort of hard-coded things. But I would love to see a tool like that. All right.
Should probably cut it.
Thank you.
So it's a fascinating conversation. Build systems are at the core of all of our frustrations. Let's give Travis one more round of applause.
Thank you.
And we'll have James Powell here in a few minutes.